Okay, so now we get to look at the relationship of the thermodynamic parameters we've been studying in the previous two lectures and equilibrium. Because the one thing I told you in the past is that equilibrium is telling you and discusses the thermodynamics of a system. So there should be a relationship between equilibrium and the thermodynamic parameters we've talked about. And so that's what we're going to address right now. We're going to look at the relationship between delta G and the equilibrium constant. Okay, so in the past we've talked about the effects that we have on the equilibrium constant when we change or apply changes to reactions, right? If we reverse an equation, we raise the equilibrium constant to the -1 power. If we multiply an equation by a constant, we raise the equilibrium constant by that very value that we multiply the equation with. If we add equations together, we multiply the equilibrium constants of those equations to derive the final equilibrium constant for the resulting overall equation. All right, and so you have like all these different reactions, right? So on the one hand, you can look at the reactions and look at them from the point of view of the equilibrium constants. On the other hand, you could look at the same equations but from the point of view of the delta G's. And the delta G's, all given kilojoules per mole in this particular parameter, they kind of provide you with some data points, right? So if you were to plot delta G versus the equilibrium constant, you find out that there is no linear relationship between them. But if instead you actually plot delta G versus the natural log of the equilibrium constant, this actually provides you with a fair enough linear plot. In this case, the linear plot is equal to y equals -2.411x minus 0.3872, which you might look at that and be like, okay, well, fine, that's the relationship. But one thing that becomes kind of that is not only interesting, but it becomes apparent once you start looking at the slope of this line, is the fact that at the temperature that these studies were done, which is 298 Kelvin, if you look at the value that you have for your slope, technically speaking, you can actually derive the gas constant. The gas constant technically in kilojoules per mole. So specifically, the value of the slope is actually the value of the gas constant times the temperature at which the experiment is being carried out. And so, yes, and that's in kilojoules per mole. So what it basically means is that what you really have in this equation is delta G on the y, you have -RT on as the slope, and x is the ln of k. So, assuming that the value of the intercept is 0, and that could very well be the case, right? This line is not exactly perfect for my data set, but implying that yes, this will probably go down to 0 if you have a perfect set of data points. What we basically have derived is the relationship between the Gibbs free energy and the equilibrium constant. Technically speaking, the delta G value is going to equal -RT times the ln of k. So let's take a look at the effects and how they relate to each other, right? So we're looking once again at the equation we used for the Hess Law in the previous lecture, for which we also obtained the delta G value. And the idea is pretty much this. If you have your delta G equation, we know that if we multiply delta G by a constant, we multiply the equation by a constant, right? But at the same time, we know that if we multiply an equation by a constant, we have to raise the equilibrium constant by the number of that coefficient. And so here I'm hypothetically multiplying delta G by that number A, and that has to be done on the right side of the equation. And the idea is that when you're dealing with logarithms, whatever number is being multiplied to the logarithm, it can be brought inside the logarithm as an exponent. And voila! This is exactly what I told you in the past. The fact that when you multiply an equation by a constant, that you also multiply delta G, all the meanwhile, when doing the very same thing in relation to the equilibrium constant, you raise the equilibrium constant to that value. This comes directly from this thermodynamic relationship. if you reverse an equation, that's the same thing as multiplying the value of delta G by -1, which means that you will have to multiply negative RT ln of K by -1. And once again, you can bring that -1 as an exponent inside of the logarithm. So automatically, multiplying or reversing an equation is the same thing as raising the equilibrium constant to the -1 power. Right? So you can see the direct correlation from the two relationships. Alright, and then finally, if you add up multiple values, right? So let's say you have two delta G values that you're adding together. That's going to equal negative RT ln of K minus RT ln of K2. And whenever you have a situation like this where you have multiple logs, you can bring them together, and the insides of the logs, in the case where you're adding the logs together, end up being multiplied. And so, once again, the same relationships that I described to you before, and I showed to you, by looking at the things that canceled out from the equilibrium expressions, it works out directly from the relationship of delta G and the ln of K. Alright, so let's do some calculations. We have the delta G reaction to 72.20, right? We can use that value of delta G to find out the equilibrium constant. All we need to make sure of, though, is that the value or the units of R match up with the units of delta G. What I'm doing right here is changing delta G to units of joules per mole so that the 8.3145, which has units of joules per mole Kelvin, will cancel out. Alright, so with that being said, we divide both sides. Okay, so you can multiply the negative 8.3145 by 298, the temperature, and then you divide both sides by negative 2477.72 to get the ln of K. And at this point, you raise e to the negative 109.86. And this ends up yielding a very small value. The equilibrium constant for this process is 1.94 times 10 to the negative 48. And what that will tell you is that if you combine water with those two gases, C2H2 and hydrogen, you are very likely to get little to none of the desired product, right? So this is a reaction that you will have to put in energy just to get it to go forward. Okay, here we have another one, right? So the value of delta G for this, now this is the formation of ethanol, is negative 174,180 joules per mole. Multiplying what's here in front of the logarithm and then dividing by that value on both sides yields a positive value. So if you raise e to 70.30, we find out that the equilibrium constant is very much larger than 1. So this reaction here really wants to happen, and is very much favored by the thermodynamics, right? And we know that from either the value of K that is much greater than 1 or the value of delta G that is negative to begin with. Okay, so here's another one. We have an equilibrium constant. In fact, this is the Ka of hydrofluoric acid. So we can plug in the value of K into the equation to find out what the delta G value is. And simply stated, you just input the numbers the way they are. Just remember that 8.3145 is in joules per mole Kelvin. So the answer you're going to get immediately will be in joules per mole. So multiply the two numbers outside the log together. Take the log of 7.2 times 10 to the negative 4. And then multiply with the outside of the log to find out that delta G is positive 179, well, technically 17,929. That's going to be in joules per mole because of the units of R. So if you divide this by 1,000, you'll get the proper units for delta G, 17.9 kilojoules per mole, implying that this reaction is not product favor, which we already knew from the value of the equilibrium constant. Okay, with all of that being said, I'll stop the video right here, and on the next video we'll talk about the Van 't Hoff equation.